Okay, so we have the pleasure today to welcome Volker Mehrmann. So Volker Mehrmann is a professor at TU Berlin. You may know him because he has done a lot of things. I first met him, I guess, when I was visiting TU Berlin for the Mathéon project and discussing about mathematics for industry. But of course, I knew him from what he was working on for a long time. He is currently the president of the European Mathematical Society, and he has been awarded of many prizes, including the Gauss Lecture, the Red Prize, and the prize also for linear algebra very recently. So we have the pleasure to have him, and in a virtual manner, but nevertheless, we will be able to hear him about modeling, simulation, control of multi-physical system, a change of paradigm.
Okay, yeah. Yvon, thank you very much. Thank you very much for the invitation to give a seminar here at Laboratoire Jacques-Louis Lyon, and I'm really sorry that I don't speak in French, but my French is not so good. I would like to talk about modeling, simulation, and control of systems, and let me start with some general remarks. So we all know that most modern technologies require modeling, simulation, and optimization and control of complex dynamical systems. But most real-world systems are multi-physics systems, combining components from different physical domains, also from different accuracies and different scales in the components. In the last years, modeling has become exceedingly automatized, linking subsystems or numerical methods in a network-based fashion. And the newest hot topic in this respect is the so-called digital twins, which means a real world system is combined with a artificial virtual system, and they permanently exchange data and run for their whole lifetime. And it's my strong opinion that modeling, analysis, numerics, control, optimization, and also data science techniques should go hand in hand. And in the last years, I have been working a lot on model reduction and will be part of the talk as well. And so let me continue with the motivation for what I'm doing. So you all know that the German government has decided to move out of nuclear energy some years ago, and recently also to very much move out of coal, which means that the energy supply has to be complemented by sustainable energy. And I show you here a figure, what is the plan of the German government to increase the ratio of sustainable energy. This is the goal. And at the moment, if you look at, for example, a day in September 2018, you can see the use of energy is very much volatile. It's changing a lot during the day and during the days. And it's very different which energy source is used. So having this in mind, a certain number of challenges appear. First of all, the security of energy supply has to be guaranteed. Different energy sectors have to be coupled. For example, green and fossil energy. For example, power to gas and gas to power. The energy conversion should be efficient. But when you do that and combine different energy sources, then you have the problem that the different components of energy networks have very different modeling accuracy. And they live on different timescales. So, and as I showed you in the picture, you have to deal with increased randomness and also decentralization. So nowadays, many people have a solar panel on the roof, or there is a farm with a windmill and things like that, and that has to be combined. And if you look at the energy system for the moment, it's mostly done in a stationary way. And so what we need is a dynamical approach. So the long-term goal would be to build a system model, which would be a digital twin, that can deal with these challenges in modeling, simulation, and optimization, and control in real time. So this is the motivation for what we are doing. And as my model problem, I will talk about gas transport networks. This is a joint research project with several universities in Germany and some industrial partners. And the question is, how do you plan, simulate, optimize, and operate real-world gas networks? So what does the gas network consist of? It's a large network of partial differential equations plus constraints. These are typically the Euler equations with temperature to describe the flow in the pipes. Then you have a network. When the different pipes meet, you have flow balance equation, Kirchhoff's laws. And then you have a lot of different network elements like pipes, valves, compressors, compressor stations, like this building here that you can see, that's a compressor station, which increases the pressure and the flow speed in the pipes. And that is really a control system. And the other problem is that we will have to do all this in real life. We will have to have reduced order models, and we will also have to have surrogate models. For example, if you look at these curves here, this is the curve that this compressor station tries to follow. So you have a curve, and then the compressor station is a huge control device which follows such a curve. And then in a gas network, you have a very erratic demand and the nomination of transport capacity. That depends on weather, that depends on prices, and a lot of other components. Also, when you want to move to more and more renewable energy, the gas network is really a perfect energy storage for hydrogen or methane produced from unused renewable energy. The German government has just put hydrogen as a focus research point. So you can see there's a lot of difficulties here. Then what comes on top of it, that such a network is huge. So this is a map of the power lines, the major power lines in Germany. But then if you go to this little node here, this looks like this. And then every little node in there looks like this. And then it comes to the households and it again looks like this. So you have a huge network. So what do you have mathematically? You have a network of coupled PDEs for the flow. You have discrete and continuous PDEs for the valves, so switching. The compressor station is really given by a complicated control system that achieves a profile. That's pretty much a pure data-based model. And if you wanted to consider mixtures of, say, hydrogen and methane, you would have to go to 3D instead of 1D. And the interesting question is, which model should you choose in which situation? How can you achieve real-time control? And then how to bring switching, delay, stochastics, and coupling to other domains. And for this, we would like to build a digital twin for the prediction and for the operation and for optimization and model reduction. So here we go. So let's look at the PDEs. The most classical model in these pipeline models is the compressible 1D Euler equations. You have the equations of mass conservation. Rho is the density and V is the velocity of the flow. X is the space variable, T is the time variable. Then you have the momentum balance, which includes also the pressure and the nonlinear term in the velocity, and a term associated with the friction. So lambda is a friction coefficient. It also includes the diameter of the pipe, and it's also nonlinear. And then you have a term that has to do with the flow when you flow downhill or uphill. So there is an H missing here, where G is the gravitational force, and h, which should be here, is the height of the pipe. And then you have the energy balance. So where E is the internal energy, and you have, and T is the temperature, and TW is the temperature of the outside world from the pipe, and KW is the heat transfer coefficient. So you have this nonlinear system of PDEs. You have this in every piece of pipe, and now you want to combine this with all the different parts of the system. So in our big research project, which is about 20 projects, we have taken this model, the Euler equation, and have created a model hierarchy. So we taken the Euler equations, and we say, okay, the velocity is small, then we just drop the small terms. We could go to simplified equation by taking that the time derivative of rho v is small. We could go to a stationary model, or we could set the temperature to be constant. And then we have such a whole hierarchy of models, including an isothermal algebraic model, which is a so-called Weymouth equation, which is just mapping inputs to outputs. And every element or node or edge in the network is modeled via such a model hierarchy, including surrogate models, which could be reduced order models of each of these components. And if you have such a model hierarchy, you can not only what we are used to in the numerical solution of PDEs is space and time discretization, but you could also do model adaptation. So you could switch between the different models. And we have implemented that for a large part of the model. For example, here's a little test network. Doesn't matter how it looks like. And we have implemented a space, time, and model error control strategy. So M is the model error, eta M is the model error, eta X is a space discretization error, eta T is a time discretization error, and the JP is the number of pipelines. And then we sum the total error over all the pipelines and put it below a certain tolerance, tol. And so, and then we optimize this cost function to minimize the computational cost. And if you do that, you can really reduce computing time substantially. We've also put this into optimizers. So we have the discretization error, eta D, and we have the modeling error, eta M, and eta is the total error. And you can see here, I hope you can read this as 10 to the minus 2 to 10 to the minus 5. So you can bring down the error by using different strategies and balancing between the discretization error and the model error. And we do this at every step of the optimization to really bring down the error. So I don't talk about the references here. They can be found in the slides which are available for you. So if this is my motivation, and this motivation in mind, one could ask for a wish list. What would we like to have from a model that we can use for these purposes? And let's keep in mind what we want. We want not only gas transport, we would like to add also other domains, as well as their coupling, like electrical power network, district heating networks, water networks, electrical circuits, mechanical systems, thermodynamics and reactive flows, chemical engineering. And what should such a model or representation do? It should work across different scales and physical domains. And we want a representation that is close to the real physics, not only for open systems, but also for closed systems. Then, as mathematicians, we would like to have nice algebraic, geometric, analytical properties, and we would like to be able to analyze the model concerning existence, uniqueness, robustness, stability, uncertainty, errors, etc. And we don't know whether our variables that we are commonly using are the right variables. Maybe some other engineers using different variables. So you would like to do coordinate transformations in space and time. And ideally, you would like to have a normal form. Then the whole thing should be easily space-time discretization, good for space and time discretization and for model reduction. And the question is there such a jack of all trades? In Germany, we have a very nice word for it. It's called eierlegende Wollmilchsau. It's an egg-laying wool milk saw. And the question is there such an animal? And the basis for such a modeling and change in paradigm is what is called energy-based modeling. So the idea is that you use energy, which is the only universal physical quantity, as a common quantity of different physical systems, connected as a network via energy transfer. So then you split the components into energy storage, so elements which store energy, energy dissipation components, elements which dissipate energy, and control inputs and outputs, including boundary conditions, as well as interconnections. And you combine them with a geometric structure, which is called a Dirac structure. And we also want that every submodel is a model hierarchy, as I presented it to you, of fine models or coarse models or reduced models, continuous or time discrete. And is there such an approach, and the system theoretic approach to realize this is the concept of dissipated port Hamiltonian systems. So this is about 20 years old. It started around 2000, and there are some groups in the Netherlands and in France, in Wanderschaft, and also Bernard Maschke from Lyon. And then there's groups, people that do software for this, Peter Breitfeld, and then the group that have done it in PDEs, Birgit Jakob and Hans Svart. And I would like to tell you a little bit about this approach and how we bring it to our use. So, as I said, for every system, you define so-called flows, F, and efforts, E, and ports, P. Then you have storage element, dissipation elements, and a connecting structure, which is called Dirac structure. And it always contains links which describe the efforts and links which describe the flows. And then you put everything together in a network. So let me start from basics. So what is a classical non-linear port Hamiltonian ODE or PDE system? That's an ordinary differential equation of the form x dot equals j minus r times the gradient of a function h, which is the Hamiltonian. I will come to this in a minute. Plus, you have another operator here, which maps the input to the state. And you have an output equation, which takes the state system here with b plus p, and then the gradient with respect to the state of h. And you may have a feed-through term s plus n times u. So x is the state, u is the input, and y is the output of the system. H is a Hamiltonian. It describes the distribution of internal energy among the energy storage elements. J is a skew symmetric or skew emission matrix function which describes the energy flux among the storage elements. So it describes how energy is routed through the system. R, which is a self-adjoint, semi-elliptic, or a symmetric operator, which is semi-definite. And that describes the energy loss in the system, energy dissipation in the system. And B plus or minus P, these two terms here, describe the ports where energy enters and exits the system. And you may have a feed-through term here. And in the infinite dimensional case, J, R, B, P, S, and N are operators that map into appropriate function spaces. I will come to this later. So this is an ordinary differential equation, control system. And the interesting question is, why should this be a good idea? And then first of all, these port Hamiltonian systems generalize classical Hamiltonian systems. That's pretty good. That's already a big part of systems in physics. And also gradient flow systems, which is very common in thermodynamics. You don't have conservation of energy anymore, but you have the so-called dissipation inequality. That means the Hamiltonian, the energy functional, at the state at time t1 minus that at time t0 is bounded from above by the integral over the input times the output. Or you could say this here is a duality pairing between input and output. And you can see if you don't put energy in or take energy out of the system, so then this inner product is 0, then you have that the Hamiltonian difference is less than or equal to 0, so that's the energy dissipation. And if you don't have dissipation, then you have equal to 0, and that's the classical Hamiltonian system. So that's the first thing. It's good that we can generate classical physics. But the really nice thing is that port Hamiltonian systems are closed under power-conserving interconnection. So you can do modularized network-based modeling. And port Hamiltonian systems are typically stable and passive because the Hamiltonian is a Lyapunov function. And this port Hamiltonian structure you can preserve under Galerkin projection and model reduction, which is also very nice because that's what we want to use it for. And then there's some very nice algebraic and geometric structures, algebraic with the coefficients and geometric with the flow, and I will come to this. And you can easily extend these systems by adding new variables, adding new systems. So that's the classical port Hamiltonian system. But when we have networks, we need a little bit more. We need algebraic constraints. For example, if we wanted to go from compressible to incompressible flow, then we have the Kirchhoff's laws, which are of flows over one node add up to 0. They could be mechanical systems with position constraints or conservation laws. Other conservation laws than energy. And so you want to define port Hamiltonian partial differential algebraic equation, PDIEs. And you want to define them in such a way that as many points as possible on the wish list of modeling that I showed you are satisfied. And there have been many attempts in the last years. It's a very, very active field. And I will show you one or two approaches that we did. So the first generalization which we did is with my PhD student, Ricardo Morandin. So you define yourself a state space and the time interval, state space X, time interval I, and you look at the Cartesian product of I times X, that is your S. And then you consider an equation which looks almost like the ODE case, but now you have an operator here in front of the X dot, and this operator can be any rectangular matrix function which operates from S to the real L by N matrices. So you could have a singular matrix here, you could even put the 0 matrix here, then there would be no dynamics. And then this term and these two terms look the same, these two terms look the same, but here I don't have X, as in the ODE case, but the function Z of T and X. And then I have a term here, R of T and X. And then I have the output equation, which looks similar. I have a Hamiltonian as before. Now these are nonlinear matrix function, and we call this a port Hamiltonian differential algebraic equation if two things, three properties hold. First of all, the coefficients have to have skew symmetry. So the matrix J, B minus B transpose N is skew symmetric. N is a skew symmetric part. J is skew symmetric. And this is, so that's pretty much automatic if the J is skew symmetric. And W, which is the dissipation term, this P, and the S, this forms a semi-definite, symmetric semi-definite matrix function. So this is also in the ODE case. And then you want that the gradient of the Hamiltonian is E transpose, where E is this mapping here, times that, and that's the function here. And the partial time derivative of the Hamiltonian is Z transpose times this R. So that looks pretty complicated at the first place, but it would be the same as before. If E is the identity and that is the gradient of the Hamiltonian, then this would be the same. And if the system would be autonomous, then the R would not show up. And this definition extends, and I will show you this, to weak solution and infinite dimension. It's a good approach. The first thing is you get the dissipation inequality. So you have that the total time derivative of the Hamiltonian, which now can depend on t and x of t, is this combined function, the z and the u, transpose wzu, and w is semi-definite, so this is greater or equal to 0, and this y transpose u, and so if you integrate it, you get the dissipation inequality. This is a power balance equation, which we get from the structure, and the dissipation inequality we get in the same way. Why did we do such a complicated structure? The reason is that we would like to have local or global diffeomorphisms. So we would like to do coordinate transformation. And the first theorem here is that if you have such a port Hamiltonian differential algebraic equation and you do a mapping, x equals phi of t and x tilde, it's a local diffeomorphism, and you choose u as well, that is pointwise invertible, then I can do a change of variables. I get a similar system where e tilde is u, then e connected with phi, and then the derivative with respect to x tilde of the phi function. The j is this combined function, the r is this combined function, and so on. And the r is combining the old r with the time derivative of the phi, and so on. And then this is again a port Hamiltonian DAE with a Hamiltonian H tilde. And to any solution, there corresponds a solution of the original port Hamiltonian DAE with this transformation. And if this is a global diffeomorphism, then the two systems are really equivalent, so there's a one-to-one corresponding. So we can do changes of variables. You can also, when you do time integration, you usually want to have an autonomous situation. You can just add t dot equals 0 as an extra equation to the system that blows up the size of the matrix here and adds here a row of zeros and to j and r and so on. And so you can make it autonomous without destroying the structure. You can also interconnect. So if you have two such systems with Hamiltonians hi, and you look at the aggregated input u and the aggregated output y, satisfying such a linear relation that m times u is n times y. For example, y is u, y2 is u1, and y1 is u2. So such an interconnector that pumps the energy from one system to the other, but every possible structure. Then the interconnected system is again a port Hamiltonian DAE, and the Hamiltonians just add and some structure. So that's good. And there's also this geometric Dirac structure. Let me explain this to you in a short moment. So let F be a linear space and E be its dual space. Then you define a bilinear form on the Cartesian product of F and E by this funny product. So you have flows and efforts, and you multiply, it takes a duality pairing of E1 with F2 and E2 with F1. And a Dirac structure is then a linear subspace on of F Cartesian product with E, such that it's also equal to its orthogonal complement with respect to this inner product. And in finite dimension, that would mean that the dimension of the D, the Dirac structure, is the dimension of the F, and the inner product is 0 for all elements in the structure. And if F and E are in D, then F are called the flow and the effort. That's the general definition of a Dirac structure. And in a nonlinear setting, you would have a state space which is a subbundle of the tangent space of X and the Whitney sum with a cotangent space of cotangent bundle of X, and then the Dirac structure over such a vector bundle is just the sum where dx is in the dx cross dx dual, and that is linear. So locally, you take the definition from before. And the definition for the flow and the effort in such a general Dirac structure is that you take a subbundle with fibers defined by such pairs of flows and effort with such a definition: F plus J times E equal to 0, where J is a skew symmetric operator, and then D is called the Dirac structure. And any atomos PHDIE of the form that I described you has such a Dirac structure. And I'm not going to, this is pretty technical here, but the trick is the flow is defined, that should be an equal here, the flow is defined as E of X times X dot, the effort is defined as the Z, the FP that comes here, that's the flows are split into storage ports and dissipation parts, the same for the efforts. The flow for the ports is Y, the effort for the port is U, the effort for the dissipation is minus W times F, and then you get this structure. And all this can be interpreted also with Lagrangian submanifolds. There's a paper by Wanderschaft and Maschke that shows it. So this was just a little bit of the idea why and how you can build such port Hamiltonian systems. We have done a lot of work on this in the last years. So we have looked at time discretization, so that the discrete time system has the same dissipation inequality and power balance equation. And so far, the only methods that do that are Gauss-Legendre collocation methods. We have also discussed controllability and observability. And there is a non-uniqueness in the representations. So there's this change of coordinate that you can do, but there's also other non-uniqueness, and that you can use to make very robust representation. And we have derived local normal forms, and we have also done operator DIE analysis. So just a simple case. Let's look at the case that we have a constant coefficient system. In the constant coefficient system, it would look like this. You have a matrix E here, and let's look at the square case. Ex dot equals J minus R times Qx, and this is with a quadratic Hamiltonian, plus the input and the output equation. And now this Z is Q times X, and the E x dot, there's no r term because you have constant coefficients. And this operator, actually this term shouldn't be there. So this operator without the k here should be skew adjoint. This inner product should be semi-definite, and this matrix should be semi-definite if we have a Hamiltonian like this. And I will come back to this for a second to just give you a few results. For example, you can easily get very nice results about the spectral properties of such an operator. So if you have such an operator, you look at the matrix pencil associated with this system, lambda E minus J minus RQ. And if you have an eigenvalue of that pencil, then the real part is less than or equal to 0. So you are in the stable regime. If you have an eigenvalue on the imaginary axis, then it's semi-simple, except for 0. And if the columns of V form a basis of the deflating subspace of mu, of the regular part, then the dissipation RQV has to be 0. And so 0 eigenvalue is really associated with something which is in the kernel of the dissipation operator. And then there are eigenvalues at infinity and 0, and they can have at most Jordan blocks of size 2. And so that's very nice. That gives you a lot of possibilities to do stability analysis. Okay, but we wanted to look at PDEs. And there are many approaches that have been taken. So one could go to take all this, what I've just told you, and go to operators, linear operators. One could go also a differential geometric way, that's called gradient flows, or the so-called generic system. Or one could define formal Dirac structures, or one can define structured PDEs with inputs and outputs. And I will give you one example here. So the abstract Port-Hamiltonian operator like formulation. Now I forget about the E here for a second. I will come back to the E a little bit later. So take the ODE PDE formulation. I have a state variable Z. I have J minus R. Then I have the derivative of the Fréchet derivative of the energy functional. And I have an input operator. And I have an output operator. A state space would be something like Sobolev space W13, living on an interval 0L into R3. The J is a skew adjoint operator. The R is a self-adjoint semi-elliptic operator. And the B is linear and continuous, for example, mapping from U du, which is a subspace of LQ into LP. And the system theoretic output is denoted by Y. And E here is a relative energy. So if you want to read more about this, there's a paper by my student, Abi Badbian, and Bernard Maschke, Chris Beatty, and myself. Now let's look at our Euler equations. They should be a Port-Hamiltonian system. And if you look at the equations that I wrote down before, there were two terms missing. These two red terms that I have here. And we need to deal with the temperature in a proper way. And that means you have to add entropy, an entropy equation. So if you increase the system like this, so you add these two terms, which are small typically, and you can typically in the modeling drop them with asymptotic analysis. But if you put them in and you add the entropy balance, then this gives you a Port-Hamiltonian system. You can also do a weak form. So you do, the other energy function is momentum squared divided by 2 times the density plus the internal energy times rho times G times H minus a term associated with the entropy, so with TW. And here we assume for the moment that TW. And we introduce the ballistic free energy, which is E minus this term here. Then the functional E becomes this sum, and the derivative you can also write down as the derivatives with respect to the density, with respect to the momentum, and with respect to the internal energy. And you can also put the operators in a block form, then you get a J form, and it takes skew-symmetric parts which relate the density and the momentum, and momentum to energy. And you have a bilinear form associated with this. And now this is probably too small for you to read, but you do multiply with test functions in the usual way and get this bilinear form associated with this skew-symmetric operator. And you can do a similar thing for the dissipation operator corresponding to the friction in the pipe and the temperature loss through the walls. It's a semi-definite block matrix function, operator function, which has a component with respect to momentum to energy, and then here the term which is associated with the dissipation of energy, and again a weak formulation. And then you have to do something with the inputs and outputs, and I'm going to skip that, but you can define output and input operators. And in the equations, we had the Euler equations before without the entropy equation. And so what you do is the operators have to be constructed in such a way that they satisfy so-called non-interacting conditions. So J times the derivative of the entropy part is equal to 0, and the R lambda, the friction times the derivative of the Hamiltonian part is equal to 0. And it's very important so that you do this, because so that the Hamiltonian, the gradient systems do not overlap. There's ways to overlap them, but then it's much more complicated. And it's very important which state variables you choose with the, in the interplay with the energy function to get the physical properties directly encoded into the system. And there are many simplifications. There are many simplifications that one can do, like going to incompressibility, but it's not straightforward. Okay. So let me come to the gas equations again at the very end. So we've modeled the whole hierarchy that we've seen in the model hierarchy before in port Hamiltonian form. We had to extend the concept of symmetric and skew-symmetric operators. We had to construct the appropriate function spaces. The input and output variables are not always unique, as I mentioned already. We have done space discretization via discontinuous Galerkin, time via Gauss-Legendre collocation, and model reduction via Galerkin projection. Let me tell you a little bit about model reduction. There is a little bit of a problem because of the constraints. So you want to replace the fine model by a surrogate PhD model, possibly also do this from input and output data, but you don't want to modify the network structure. And the Kirchhoff's law, so the balance equations must still hold after reduction. And other constraints if there are any. And what is model reduction? You take a system, so I've written it here in an implicit form, depending on the state, discretized, the input, the derivative of the state, and you have initial conditions, and you have an output, nonlinear, and you want to replace this system by a smaller system, FR, where the dimension is much, much smaller. The output errors should be small. You should have global error bounds and preserve physics. And you want to have a stable and efficient method. So let me show you this for port Hamiltonian ODEs. So you have such a system in the simplified form where the gradient is q times x, quadratic cost function. If you have that, you make just the standard ansatz that X is projected into a finite dimensional space VR, and that QR, Q is the derivative of the Hamiltonian, QR XR is projected to a small energy function, which is W times Q. You do a congruence transformation with W on J and R to keep symmetry, and you make sure that W times V has this orthogonality. You do this with the input function, and if V and W are appropriate orthonormal basins, then you get again a port Hamiltonian system. If you want to do this for the case when you have an E here, it's a little bit more tricky, because you can do essentially the same. X is put into a subspace, E is projected from the left and from the right, Q is projected from the left and from the right, J is projected in a congruence way, R as well, but the constraints may be destroyed. So you have to use clever projectors that keep the constraints. And let me go to a test example. So this is one of the systems in the hierarchy. This is the propagation of pressure waves on the acoustic time scale in such a gas networks. Take a simple network, here, 4 nodes and 3 edges. You form a graph with vertices and edges given by this. You write down the conservation of mass and balance of momentum. Your Z variable is the pressure and the mass flux. You get this transport equation here in first order, where the coefficients have all the physical properties of the pipe, like friction and everything in there. Then you add the Kirchhoff's laws, so the conservation of mass and momentum, and you add inputs and outputs. The output is the mass flux in and out of the network via the exterior vertices, and the input is the pressure on the edges in the beginning. You take initial conditions for pressure and mass flux, you take a quadratic Hamiltonian, and you use this for Galeckin projection. And what you get is a system which looks exactly like the one we had. Q is the identity, that's good. E is such a singular matrix with 2 mass matrices here. J is such a block tridiagonal matrix, which is skew symmetric. R has just the friction damping term. Input is just here in the second equation. And in a paper by Egger and Kugler, they have done the analysis of convergence, the error estimates, and the stability. And for this, you can do everything that I suggested. You can do model reduction via moment matching. You check the well-posedness, the conservation of mass, dissipation inequality, exponential stability. We have constructed special Krylov methods to satisfy the algebraic constraints. And we had to add a little bit extra to guarantee the geometric structure. It's a so-called cosine sine decomposition. And the reduced model satisfies the same condition. We don't reduce the constraints, and we have efficient methods to compute these projections, and we've shown error bounds. Here's just a few little examples. So we have the pressure when you refine the mesh, the pressure converges to the true wave, and this is the velocity of the first component, the velocity of the second component. So we have good convergence here. And here is what the reduced model after model reduction looks like once we've corrected the pressure. If we don't correct the pressure, we get such garbage here. And here is one a little bit more realistic example, and I'll show you these figures to show you. So in the first row, we have taken dimension 2, 5, and 10. We started from 10,000. We have 2, 5, and 10. And the blue is the truth, and the red is the approximated model. And if you add more and more damping, you can even do it with 5 in a very accurate way, or with 2 in a very accurate way. So you can get reduced models which are very small, and you can use them for control. So let me conclude. We have this wish list. And if you look at the wish list, then Port-Hamiltonian partial differential algebraic systems are an ideal class of problems, and our wishes can be fulfilled. But there are many things to do. The real-time controllers, we're working on that, and optimization methods. Other physical domains, we have been doing power networks, heating networks. We've done electrical circuits. What we have not done is to incorporate stochastics in a good way in the model. That's an open problem. Stability analysis, we've worked on it in the constant coefficient case, but we would like to do this in the general case. We've done some error estimates, but no more is needed. Preconditioning is needed. Data-based realizations and software production, we're working on this. And recently, this stuff goes into a big research project on creating digital twins in the Werner von Siemens Center, Berlin, which is a co-project between industry and the technical university. And with this, I would like to close and thank my sponsor, in particular, the ERC Advanced Grant, which really started this whole development for me. The Research Center Matteon and the Einstein Center and the Excellence Cluster Mass Plus, and several collaborative research centers, and the German industry, Ministry of Science and Technology with the project IFA. And if you want to have more, you can go to my website and find all of the papers there. And at the end, I would like to make a little bit of an advertisement. Hopefully, depending on Corona, we will have a thematic semester on energy-based mathematical methods for reactive and multi-phase flows. And please have a look in the Mass Plus Center for student conferences and other conferences. Thank you very much.
Okay, thank you, Volker, for this very inspiring conference, and very nice model for and appropriate for a system that we can encounter in industry. So if you want to ask a question, please raise your hand, and I will be happy to give you the floor. Maybe to start, I have one question concerning the non-interacting condition that you quoted on page 47. Is it natural? Is it easy to? You said it is very important to have it. So
yeah, it is. It is one way when we try to put the link to this generic framework. So this is a differential geometric way of dealing with thermodynamics, and there we needed that. Whether it's really needed, we don't know. At the moment, I'm debating with myself whether we really need it, but it would be great if we could drop it. So far, I don't know. In the generic framework, you have them. So if you want to really put a one-to-one correspondence to the generic framework, you should have in your formulation these non-interacting conditions, but maybe we can be more general and drop them.
Okay. And so is it natural, and is it easy to get it? In particular, when you reduce your system, is there a natural way to maintain this non-interacting condition?
Yeah, the first question, yes, it's very natural in the way, if you have gradient flows, this is always the way it is set up.
Okay.
Whether in the coupling it's really natural, I don't know. I actually don't think so. But we couldn't prove the results to the link to the generic without constructing the operators in such a way. And it's mainly the boundary operators which make trouble here. How you put the energy from the boundary into the system.
Into the system, okay.
Concerning the model reduction, yes, you have to look at these constraints at the boundary condition and project them in a proper way. That may or may not be easy. In the We've done it for reactive flow in a new turbine. There it was easy.
Mm-hmm.
We've done it for these power networks and gas networks. There it was easy. But if you have a Maxwell equation or a distributed control over a system, I'm not so sure how easy it is. So mixed feelings.
And also on page 54, is it related? You spoke about having the proper projector for the Galeckin approximation. So is it related to this non-interacting condition, or?
It is partly related to the non-interacting condition and partly related to, if you have Kirchhoff's laws, for example, at a node, and they give you the E term here, this would be the network matrix, then afterwards you want that you don't gain or lose energy at a node. So the algebraic conditions that the sum of the flows should add up to 0 at a node condition, that has to be guaranteed. And so the projectors have to satisfy that. And that is extra work that you have to do. I did talk about it in Providence a little bit, but it's an extra work, and it's not trivial to get this. And if you have other constraints like conservation of momentum or things like that, and you want that the reduced system is also conserving momentum, then it's an extra constraint equation on top of the Porter Hamiltonian structure itself, and then you have to work for it.
Okay. I have another question concerning the adaptivity of the model. So at the beginning, you spoke about an error for the discretization and for the model. So you have an error estimator for the model? And
yes, we do. Actually, we do an error estimator when we do this simplification here for each step here. Mm-hmm. So setting something small to 0, we say, okay, what sensitivity do we have there? What effect will it have on the results? And we always compare with the Euler equations as the ultimate model, which we assume to be the truth.
Okay.
There could be another truth, which is a more complicated model.
Yeah.
And so in each of the cases, we look at the sensitivities, what happens if we set the temperature to be constant, and we compute first order sensitivity terms in each of these components. And for example, when we do the optimization, in this case, we look for a feasible solution. If we get a feasible solution with a low model, fine. If we can't get a feasible solution to a certain tolerance, we lift the model up, either go to finer discretization or a better model, assuming that we can control the truth. Mm-hmm. Or optimize the truth, and then we can show that if we can optimize the truth, this will give you an efficient method. So we can always bring the error in space-time and model below a certain threshold.
What is a feasible solution?
So, for example, you want to minimize the compressor cost.
Okay.
So you say, I want to minimize the cost. You want to do a step into, say, the gradient direction, and the gradient goes up. Then you don't have a feasible step. So when the gradient goes up, then you reduce your step size, or you reduce your time step size, or you reduce your, or you lift the model.
Okay.
So it's really in the optimization code, the feasibility.
Mm-hmm. And so you are able to balance the discretization, the model, and maybe.
Yeah, you can see in this picture that I have here, you can see that it's really the discretization error here, which very much drives the total error. Okay. The model itself is much below. So we could take a more coarse model here. So we could put a surrogate model here to put it here. And this is what was our motivation, that we wanted to use the most simple model, the most cheap to evaluate model with space-time adaptivity and also model adaptivity.
Okay. Okay, very nice. No question? in the room? Okay, so it was crystal clear. So you spoke about the Gauss-Legendre collocation in time also.
Yep.
So for the discretization, so collocation in space generally make the system less symmetric and less.
Yep.
So, but for collocation in time, you are able to maintain all the nice properties of symmetry and
actually, if you have a quadratic Hamiltonian, you can show exact representation of the dissipation inequality or conservation of energy. And if you have a non-quadratic Hamiltonian, you get it up to the order of the method.
Up to the order of the method, okay.
And then Gauss collocation has the right sign. So the order has the first term in the order correction is going into the right direction. If the higher order terms dominate, then you have a problem. And
okay. If the system is not
yeah, if the system is that bad. In space, there's just a new paper by Herbert Egger from Darmstadt who showed that discontinuous Galerkin in space in general will work for this type of methods and preserves the structure.
Okay.
Even on the more general EAE setting.
So if no more questions, I have finished my list and no, nobody. Okay. So thank you a lot, Volker, for this, again, for this very nice presentation. So there are all the references in the paper, and the slides are on the website of the lab.
Yeah.
And let me remind you also that the presentation has been recorded, and it will at the end of next week be available on the YouTube site of the laboratory. Okay. Thank you, Volker. Again, bye-bye.
Bye-bye. Thank you.
Bye.